So we continue with our previous sessions and the discussion where we talked about netlist concept of netlist. We have seen that there are design teams. We started with the logic design team, just to summarize again, and then we had the circuit design team, right? And you being the team of the physical layout engineers or physical design team, uh, I stated that you need to know what is happening in these two teams, what are the processes they are performing and all these things. So they are quite interlinked to each other, logic and circuit design teams. And we saw that there is in logic design team there are two ways to represent or understand a schematic. One is the logic diagram, as we've seen here, by means of gate, and one is the transistorized circuit diagram. So what they do, they use the structural they use the Verilog hardware description language, which is a structural or behavioral code by which they describe the logic. Okay, and when they write some coding, that coding is basically called as netlisting. For the example, this schematic, the logic level is netlisted, or if it is a transistor level, it will be netlisted. For what? For the two purposes: for the purpose of simulation and for the purpose of verification. So basically, the compiler, RTL compiler, usually it is called, that will be used to actually simulate that. The waveform for this particular logic will be generated by the EDA tool, and it would be verified by an engineer or team of engineers by analyzing its response. They will check what is designed is accordingly behaving, it means the behavior. They will check about the timing constraints, and the tool will also generate the delay and power details of that particular logic for a given technology. So usually when you describe this kind of when you use the Verilog HDL to describe some logic, we call that this is a technology independent structural description. Why? It means you can, this is quite generic. Once the logic is described, as you can see here, there is a logic described for this particular schematic. So it is technology independent. It means it is applied to any technology node that the designer is designing the logic for, from 10 nanometer up to 100 nanometer, depends on that. So it is technology independent because the generic gates will be used by the ADA. There is not specific IP that is we are asking the tool to use or we are using inside the tool. The generic gates will be used, and the actual gate implementations we don't specify it. We don't want this logic to be implemented using a specific tri-state or transmission gates or etc. The tool will decide it. So that is auto set. So that is a logic netlist, and I also explained in the previous session that there is another way, is again the structural Verilog HDL. So that this particular netlist is called as transistor level netlist, and I help you to explain and understand what is the meaning of this netlist, because this netlist will come to the one down level to the team of the physical engineers, and the physical engineers should have a basic understanding to understand how the netlist is explained, how the netlist can be read. Sometimes the physical engineers can also have access to the schematic. For example, it is shown here a particular circuit for a specific logic, or they can be given just by a netlist. So they should be able to understand what this netlist means, what are the lines, and what is the syntax. It's just a code. So we'll see, I explained you how to understand this netlist. I said that this is a transistor level netlist where each transistor in this circuit diagram is described the way it is connected. So there are NMOS transistors as I see in the circuit, there are PMOS transistors as I see in the circuit. I see there are inputs to this circuit A, B and C, and I see there is an output called as C out. So the logic designer, they will just describe and write the code with this particular standard. They will say, okay, they are designing a module for a carry circuit of the adder. So they define input logic, A, B, C are the three inputs. Output, they name it as a TRI or try, and they call it as a C out. Then they say that this TRI is another logic level, and they say that there are four nodes, I1, I2, I3, I4 and Cn. So we can come to schematic and see where these nodes are. So I1 is the node over here, I2 is the node over here between N5 and N4 transistor, and I3 is the node right over here. It's just like where the voltage logic level will switch. So, and then they describe, okay, I have a supply which is ground, and I have a supply 1 which is VDD. After that, I describe, if I am a logic engineer, I will just describe the transistor, and this is the syntax for that. What it means, I am naming the transistor type, I am calling it tran if 1 to understand that this is a NMOS transistor, and I call it name N1. So this is the type and this is the name. So I am using NMOS transistor, name is N1, and in the parenthesis I describe the syntax and indicate how its terminals, how many terminals it has, 3 terminals, which is drain, source and gates. So I am telling that to which node in the circuit these drain, source and gates are connected. So I see that, okay, my transistor is NMOS, name is N1, the drain, source and gate are connected to the node I1, ground and A. So I want to verify this. So let's see, this is N1 transistor. I see that this is NMOS, of course, because the PMOS is indicated by the bubble. So I see this is NMOS, and its drain is connected to the node I1, look here. Then its source is connected to the ground potential, and its gate is connected to terminal A or port A. So there are ports also, input ports and output ports, right? So this is how I will describe each transistor in the circuit. Basically, as a logic engineer, when I am writing this code or writing this netlist, I would actually look at the schematic and I will keep on writing this code one by one. So similarly, let's take an example of tran if 0. It is a PMOS transistor. If tran if 1, they are all NMOS transistor, and I am naming them by N1 up to N6. Then PMOS transistor name is type is tran if 0, and I am naming them P1, P2, P3 up to P6. And again in the parenthesis, I am telling how these drain, source and gates of each of them are connected. So this is and then I simply end the module. So it's basically a code very similar to the way you write C and C++ code. So this is basically generating a structure using Verilog transistor level netlist. Okay. So we saw the two ways the structural Verilog can be used to generate logic level netlist and the transistor level netlist. So we generated this description in either way, but if you recall from the previous session, I explained to you that we want to do this particular task with the intention of getting the estimate of the delay and the power of that particular logic that we are designing. I told you that we are designing the logic, but as our role and our goal was to estimate how much is the power consumption and what is the delay, because that will help us to understand what is the maximum speed at which the circuit that we are talking about and we are designing will operate. So from these two netlists, if we carefully look at that, we still don't have any information which is required to determine speed or power of the gate, right? Nowhere, whether in the transistor level netlist or the logic level netlist, we are just telling that, okay, use the general gates from the library, generic gates, and there is no information by which we would get the information about how much power will be consumed when this circuit will be designed, and what is the maximum clock that this circuit can operate with, right? We don't have any information from this netlist. So that is the drawback of Verilog HDL. So basically Verilog HDL is called as gate level language. It just describes the behavior, all the structural of that particular logic. And if we can also go to generate another transistor level netlist, and so we call it as a Verilog is also a switch level language. So that is just helping us for the structural description, giving a particular levels of details, not too many details, especially when we want to estimate power and the speed of the circuit. So what to do in such case? Is there any way we can have another description when we are designing particular logic or we are designing a circuit? Is there any way we can understand how much will be the power consumption and how much will be the delay? So for that we need to specify the size of the transistors and the stray capacitances. What is the meaning of the size and transistors? It means, if you recall, I have explained to you from the previous slides, from the previous sessions, for our transistors we always talk about the W by L ratio of the transistor, if you recall, right? We always talk about the W by L ratio, where W is the width and L is the length of that. So I also explained you that, okay, I have a metal on this particular transistor. There is somewhere right here. Let me draw another way. I told you that in the previous session, our MOS transistor, here is a metal or polysilicon. There is a SiO2 in between, and there is a P-type silicon. So I have a metal oxide and semiconductor, and I said that this is basically a two capacitive plates separated by a dielectric or insulator. That is what I am calling it, or I am modeling this as a capacitor. So I said that my MOS transistor can act as a capacitor. So basically I would use so many transistors just like shown in this particular circuit, as you can see that. So each can be modeled as a MOS capacitor. So it means they will act as a capacitors, because this output of this circuit is driving to the input of this circuit. So the load here are the gate capacitances, and there are some other capacitances also that we'll talk in more detail as we go ahead. So what I need to do is that I want to specify the size of the transistors to estimate the power and delay. That is possible if I mention in the netlist information about W and L, if I specify that. And what about the stray capacitance? I am using the MOS structure, so each transistor can be modeled as a capacitor. It means they have the stray capacitance. So these stray capacitance, or you can say that these capacitors, are inherent in the circuit diagram. Although we don't connect any external capacitor, you don't see any external capacitor here. But where are the capacitances then? These transistors are itself all the capacitors. They are inherent capacitances. So when I have information about these two parameters, the netlist generated will help me to estimate power and delay. So we'll see how. I stands for simulation program with emphasis on the integrated circuit. I repeat again, SPICE, simulation program with the emphasis on integrated circuit, IC, right? So this was the language invented and created at the University of Berkeley several decades ago, and ever since this has modified. There are several open source SPICE tools also available to learn and practice. Usually we teach them, our students here, using open source tools as well, because the main foundation is the knowledge, and we encourage them to use the tools later in their professional level. Okay, so let's see how SPICE can help us to avoid the problem with the Verilog HDL and help us to estimate delay and the power. So what we see here, same circuit diagram, but now I am using not the Verilog HDL, rather I would use the SPICE. So I need to understand what is the syntax, and this syntax also need to be understood by the physical engineers or layout engineers, because when they are generating the layout of a logic, the team of the layout engineering, they are basically having access either to the logic circuit, either to the logic diagram or the circuit diagram or the netlist, or all of them or any of them, right? So the specification at the transistor level circuit, for example given here, at the circuit level can be described like this. So they, first of all, they say that this is a blank box or a blank box, in which they would say that they call it as a sub circuit. Okay, this is a sub circuit. Why? Because this is a small part of a big circuit. Like I told you in the previous section, this is a carry circuit diagram, which is a part of full adder circuit, right? So they will say dot sub circuit. This is just a syntax. What is this name of the circuit? Sub circuit carry. How many inputs it has? A, B and C. A, B and C. What is the output it has? C out, and power and the ground, that is the supply rails. Then I start describing the transistor syntax. So how the transistor syntax is usually done is given right over here. So what I do, mname, it tells me this is the transistor, okay, and it tells me whether it is NMOS or PMOS. So if I write MN1, for example here, it shows me, it tells me it is NMOS, right? Or it just say it's a MN1 is the type of the transistor, just like structural VHDL. Then I have three terminal, drain, gate and source, and obviously body. So remember, in Verilog code we did not talk about the body. Okay, where is the body of these transistors and where it is connected? Can you recall that? Because this is now important for you to understand, even for the layout. So I have explained to you that this is an NMOS. So this is drain, gate and the source, and the body is connected to the source, right? So you see now there is a syntax here, drain, gate, source and body. Okay, then a type. What is this? NMOS or PMOS? So that, and then comes width. I specify the physical dimension. Then length, I specify the physical dimension. Then AD is the area of a drain. Where is the drain area? Where is the area? I know that. Here is my P diffusion or N plus, and this is P substrate, right? So this is basically a drain, this is basically a source. So the cross section area, how much is the area? You remember the session on the fabrication, how this area and well everything got fabricated with the ion implantation and with the diffusion process. So I need to mention that. Then with this I need to mention AS, the area of the source. So you can see now this kind of circuit description actually help us to actually describing the physics of a transistor and hence the physics of a circuit. So you have accurate and very much details how the circuit is behaving, and because of that we would be able to calculate all the parasitics. What are the parasitics in this circuit? Parasitics are, I told you, the capacitances inherent or already there with the circuit. I don't have any external connected capacitor, I don't see. So where are the capacitor? Because I said that I can model my MOS as a capacitor, right? That's nothing but essentially a capacitor. So if I connect external capacitor, for example, to the load here, then I would say that okay, my circuit also have capacitance. What about the resistances? Do I have any external resistance? Then where is the, if not, if I don't see, then where is the resistance coming here? Can anybody tell me?
Depending on the width of the drain or source, there will the resistance varies, sir.
Right. For example, I am having the charge transport here, electrons are also. Obviously, it's a semiconductor, so it has a resistance, right? So that is happening there. So another resistance is there are 12 transistor or n number of transistors. Are they connected just like that, or they are connected through wires? What is the wire we are using? How are you connecting them together? Can you recall? Go to the session of layouts.
Using tri,
Using mask.
tri yes. No,
Not the
using
mask, using the
polysilicon, sir.
layer. Yeah, poly gates are connected using polysilicon. That's correct. Very good. And what about the other layers available for connections?
For the drain and source, I think they use metal layers.
Yeah, metal layers. You remember that? You recall we have metal layer that was used to connect the transistor. For example, do I need to explain you again? You remember that we had um, this transistors, right? So if you see that there was a transistor, and we said that here was a drain area, here was a source area, and that was a polysilicon. And there was another transistor right here, and again you have this polysilicon right here. So these two polysilicon got connected through the metal. Okay, drain got connected to the VDD, so we use the metal for routing, right? So metal has some resistance also because they are wires, right? So the wires in the circuit will actually give the resistance in the circuit. So parasitics, remember one word, parasitics or stray are very important for the layout engineers. They need to understand in the given circuit when the physical layout will be generated, where are the parasitics and how to minimize them. So basically engineers in the layout team, they try to put all cells very close to each other so that the parasitics can be minimized, because if R and C can be minimized, then what happens?
So the
Yesterday
only
session.
parasitics that are there in the die will be the resistance and the capacitance, right? Only
Say,
these two.
say again.
The only parasitics that will be considered in the die will be the resistance and capacitance, right?
Yeah,
Inductance,
parasitics are the resistance and the capacitance. Yeah.
there will be no effect of inductance, or like it doesn't exist, or it's not considered.
Well, at low frequency is not pretty much concern. At high frequency, there are some called antenna effect, electromagnetic effect, and all that. So we can just say in our understanding for now in this specific course, we'll say R and C. Okay. So
Yes.
I help you to understand the netlist here again. So M1, it is a NMOS. The drain, gate, source, and body. They are connected to the nodes I1, A, ground, ground. So let me see. Okay, it's an NMOS transistor, and the drain is connected to I1, I see. Then comes gate is connected to A. I have shown small a here, but there are capital A, but doesn't matter as long as you are consistent. Then its source is connected to the ground, and the body I have shown you always tied to source. So hence source, since source is connected to the ground, the body is also connected to ground. So I got this NMOS here. Then what type of transistor it is? NMOS. So I write here. Then width is 2 micron. 2 U is 2 micron. L length, channel length is 0.6 micron. AD is the drain area, that is 1.8. This is the drain
Pico.
area.
Is
Pico.
it pico?
Pico. What is the unit? Pico meter square area is the area. Pico meter square. Source area 3 picometers square, right? So it is how I describe the syntax for one transistor. Similarly, I will do it for all the transistors. So very simple. And you can verify yourself also all these transistors. Just see the schematic and see how these nodes are connected, and that is how whole circuit diagram is done. So like I said, the body connection wasn't listed in Verilog, but now it's required for the SPICE, because we are talking, basically SPICE is helping us to describe the physics of the transistor, so that all parasitics will be taken into account when the circuit will be simulated, and during the verification, when we verify its performance, we can get the information about delay and power. For example, if I have external capacitors, how will I define the syntax? The name of the capacitance, C name. It could be C1, C2, whatever. And I will then tell through the syntax at which two nodes it is connected, node 1 and node 2, and the value of that capacitor in farad. So for example, if I connect a capacitor here, can anybody tell me the syntax for that? Because layout engineer need to understand how the netlist to be read. So if I have a capacitor here, can anybody tell me the name of the capacitor is C1? So what is the syntax?
VDD C1
So
and
C1 is connected between,
C out.
correct,
Ground.
ground, and the
Ground.
value is, let's say I said is 1 picofarad, so I will say 1 picofarad. Okay, that's correct. Let's say I have a resistor here, 1k R1. Tell me the syntax.
CN.
Cn, correct. R1 is connected between Cn and
Ground.
ground. What is this
One.
value? 1k.
1K.
Simple, right? So simple, that's correct. So in this description, the MOS model and the model for the capacitance and the resistance, if they are there in this SPICE netlist, will calculate the parasitic capacitances inherent in the MOS transistors. Why? Because we have specified the transistor dimensions: width, length, area of a drain, area of a source, etc. So once these parasitics are calculated, R and C's in the circuit are calculated, there we can get the estimation of time constant indicated by tau, right? That is the RC, that is the delay. Okay, we'll see in more detail as we move ahead in the course. So that's all for the circuit design team. We explained, we talked about logic design team, we saw what languages they use, we saw how they describe their logic or circuit using structural Verilog and the SPICE. We saw some limitation about Verilog. So we also introduced SPICE, and I help you understand how SPICE helps us to describe at a deeper level, and I also help you to understand how to understand the netlist syntax. For a layout engineer, it's important. And now comes your area, because you are a PD team. So first thing is that for floor planning in the physical design. So it's a big topic, but the purpose here is to give you a broader understanding first, and as your understanding will develop, and accordingly I will provide you with higher details. So what is the floor plan? Basically, essentially it is just like you have a flat you just newly purchased, and that's the hall of your new flat or apartment, and now you entered the house or flat in an apartment, and you want to decide which section of this is the area that is given to you by the construction builder. And now as a owner of this flat, you have to decide which area will occupy the sofa set, which area will occupy the dining table and TV and etc. All the your materials in the house, right? So just analogy. So from the VLSI engineers will understand the floor planning is basically to estimate the area of the major units in the chip. What are the major units in the chips? Architecture. For instance, I am explaining you the floor planning of the processor. It's, let's say I am designing the processor chip. So basically floor plan helps me to estimate the area of the major units in that processors. What are the major units? In the memory, arithmetic logic units, data buses, input output interface, mixed signal logic, mixed signal circuits, analog RF. I explained you that. So it will help me to estimate area and define, it helps me to define where I can place them, right, which section. So now why this floor plan is essential? Because it helps me the chip area budget. Bigger the chip, expensive, bigger the chip area, it would be expensive. So designer, my job as a designer is to pack more and more logic in a given set, in a given dimension of area. I cannot have arbitrarily large area. Whatever the area is assigned, I wish to pack as many logic blocks as possible. Also, I want to estimate when I will do the routing, the wire length should be minimized between the that wire. What is the wire required? Because all these blocks are interconnected to each other through metal routes, metal wires, as I explained. So I am giving you a very broad overview and general introduction for this now. And also the wire congestion should be avoided. What is wire congestion? If you recall, I told you in the technology you will have many metal layers. Why are they given to you? They are given to you M1, M2, M3 and M4. It's just like in a modern city, smart city. Excuse me. If you see, when the bridges are constructed in the smart city, there are there are bridges on top of each other. So they are called level 1, level 2, level 3 and level 4. So similarly, you can look at the chip from the top level, or you can see the cross section also I have explained to you. So metal 1 to metal 6, if you have 6 layers of metals, so you can use each metal for routing many millions of blocks, obviously automatically and some custom way, to avoid the traffic congestion, because that is what is required in the chip. So this initial floor planning, when I am using the word planning, helps the designer, especially the physical team, to loosely define their logic, where to place each blocks and all that blocks. So you see here, this is basically the area, core area. I will call this section as a core area, where all logic will be placed. Processor, memory, data bus, control unit, input, output interfaces and so on. What are these rectangles here? 1, 2, 3. They are called input output pads. So I have explained to you that what input output pads, when the chip will be laid out, the final chip layout will look like this. That is a block diagram, and this is a layout of the chip. So they are basically, you see now, these are the pads. These are the pads. These are the pads. These are the pads here, right? So what you see here, I have 10 pads in each section. So total, how many pads I have here?
40.
40 pads. 40 pads. And now have a look at that. So the chip flow plan, this is for the chip, this is the chip flow plan for the processor, including the pad frame. So pads are also given. So you can see now the core logic is sitting in this square box, and the pads also have a comparable size, right? So now the top level blocks, I said, okay, here it's shown control, then data path. I may have ALU, I may have registers, I may have memories, I may have IO logics and all that, right? Then in between there is a space left. So this is just an example of a processor chip flow plan. So this space can be kept there. That is called wiring channel. That is located between these two blocks to provide a room, sufficient room, so that the control signals can be routed to this block, from this upper block to the bottom block. Just an example. And now you also see the dimensions are mentioned here in the blue color, so we'll understand what these dimensions are. That so first of all, the pad frame includes 40 input output pads which are wired to the pins on the chip package. Here you see there'll be pins as we see the package chips, so these pads will be wired to the chip pins when it is packaged. So for example, I have 40 pads, so not all of them I will use for signals. As an engineer, I will keep, for instance, for in this example I have used, for example, 29 pads for the signals, and the remainder of the pads I have used for VDD and ground. I will show you in a moment which pads I have used and where I have used them for VDD and ground. How much is the chip area now? That we want to estimate. So can you recall the basic idea I had given to you to estimate the layout size? What is that idea, or what is that concept?
Width and length.
No, when you draw the layout, we have understood the session on the layout. So if you have done the exercise also, so let's say you have drawn and completed the layout for CMOS inverter for a given technology. I had given you this assignment and I had asked you to estimate the area. So how did you do that?
Using lambda and
Correct, right? So let's say this chip is to be designed or was designed using a technology node 600 nanometer. See here. And this whole area including the pads is now the die area or chip area is 1.5 meter square. It's a rectangle meter square. So can you tell me now, the die is this silicon die, if this is a silicon die, how it is 500 lambda each side? You can see the 5000 lambda vertical, 5000 lambda horizontal. How they got estimated? Again, you can refer to this sentence. The technology is 0.6 micron and the total die size now is 500 lambda and 5000 lambda each side. How did that number come, 5000 lambda? The chip size is 1.5 millimeter by 1.5 millimeter. In other words, 5000 lambda by 5000 lambda.
depends on the how many transistors are required are there in the.
No. It seems like you haven't done exercise, right? You need to do the exercise because that's very important if you want to actually get a good understanding about this process and you want to advance in your career and all this. So you need to perform all the homeworks, assignment. So you see what was the lambda rule for the CMOS inverter layout? I explained to you.
That's equal to L by 2.
That was, I told you, lambda is the process parameter or some parameter that helps us to estimate the cell size that we are designing or that we are drawing using the layers in a given technology. So L is the channel length or the physical feature size, and half of that
lambda will be 300.
Half of that would be lambda. Lambda is L by 2 if you recall. So if I say I have a feature size of 0.6 micrometer, so lambda is 300 nanometer, right?
Yes.
And I have said to you that okay, this final using this technology 1.5 millimeter vertical and 1.5 millimeter is basically the chip size. So this number is nothing, 5000 lambda. Lambda is 300 nanometer. So 5000 multiplied by 300 nanometer is 1.5 millimeter. Is it correct?
Yes, sir.
Right. So this is how they estimate the right. So you can see also this is the die area, but logic which you have designed, that is just sitting in this area, and the rest of this area is just occupied by the input output pads, as you would see in this diagram also. You see now, right? So tell me, what is the area they, how they floor planning means? They will estimate the area for each and each. They estimated the area for the whole chip, then they estimate the area where the core logic is sitting. This is 3500 lambda, this is 3500 lambda, in which the whole processor logic is sitting. Now inside the processor, I told you there is micro architecture. Micro architecture would be Pentium, whether it is Pentium processor, whether it is Core 2, where it is Core i7, etc. So in that they defined which logic is sitting where. So here they are saying that here is the logic for data path. Here it may be a memory, ALU, and etc. Here is they have defined the control and the controller. So for this also they have estimated the dimension. You see 2550 lambda, 1900 lambda, etc. So even for a single CMOS inverter somewhere placed here, 2 lambda by 3 lambda, designer first estimate that size, which was your exercise I gave you. So you said that for a given technology my inverter cell took this much size. Using those inverter cells or cells that you laid out for NAND gate, NOR gate, inverters and tri-states or buffer, you basically call them from your library, or vendor or manufacturer provides you them ready-made in your library, and you place them. You decide as an engineer where to place them to create a bigger logic. For example, using the NAND NOR logic, you would want to create the flip-flops or latches. Using latches and flip-flops, you would create the layout of counters, shift registers. Using the layout of those counters and shift registers, you would want to create a logic for random access memory, RAM, or read-only memory, ROM, etc. So this is how you see, you start with a very single cell, inverter, NOR, NAND, and then you keep on creating, by interconnecting them together, you are creating a bigger logic. And for each cell, you estimate the area, then you are able to estimate the area for bigger module, and then you are able to estimate the area for your microarchitecture, and finally you are able to estimate the whole area for your architecture, and hence the chip. So finally this is the layout of the processor. You see that. So what is to understand, each pad is 750 lambda by 350 lambda, the pad size, right over, don't get confused. So lambda is L by 2, whatever the feature size given. So because this is the size of the pad, the maximum possible core area inside the pad frame, here inside the pad frame, is 3500 lambda by 3500. So you see now, this is the 3500 by 3500, as I said. Rest of the area taken by the pads right here. So such design, if this is the case and the layout will look like this, such design is called as pad limited, because the IO pads sets the chip area. You cannot do, as an engineer, physical engineer, you cannot do much. That is already defined and you have to comply with that. But many of the commercial chips today, they are also called as core limited. It means the chip area is set by the logic excluding the pads. First you will talk about and set and define your chip area that will be occupied by the logic, and you don't care about what is the size of pads, no matter, they will come later. Okay, so now you see here metal 2, I said that out of these 4 zero pads, 10 on each side, I want to use few of them for the signals. You see that signals, like these are the metal wires, they are all connecting to the pads there through these connections, right? These are the metal wires here, and I am using few of them for VDD and the ground. Not all 40 I will use for signals, because 29 I have used them for signals and remaining I use for VDD and ground. So can anybody tell me, like, I use the metal 2 wire, it means I had in this technology I had metal 1 and metal 2 for sure. So 2 metal wires. So metal 2 was used for VDD and ground rings. So this squares after the pad, just inside the pads, this and this, that is called as VDD and ground rings. And how do you identify them? Plus and minus sign. So plus indicates VDD, minus indicates ground. You see all 4 corners you have plus and minus, plus and minus. So they are all supply rails all over the chips, in all 4 corners, 4 sides, not the corners of the chips, that is providing supply to this processor. And there is also a signal wires and accordingly. So that was for today's session, about giving you a brief overview about how the floor planning is done, and how this is an example layout for a processor. It could be any architecture that you would like to understand. Any questions you have?
So how can we find out the chip area if you are given with a layout?
If you mean if you are given a ready-made layout by somebody else, right?
Suppose we are considering the layout of CMOS inverter.
Yes.
How can we find out the chip area from that?
Did you ask me, like, you are given a full chip like as shown over here, and you want to estimate how much is the area of this chip? Is that your question?
That is also correct.
Yeah, so for example, you are given or you are shown example layout like this, and you are asked to estimate the chip area. The EDA tool, when you open the layout file with the help of a tool, there are measurement scales available. You can just draw the vertical and horizontal scale right over here to estimate the area, to calculate that. You can just draw the scaling horizontal and the vertical. The numbers will come here.
Annually, how can we calculate that?
And how can?
Annually, if you are doing, if you are considering CMOS inverter circuit layout, how can we calculate the chip area?
I think you have submitted me the inverter layout.
Yeah,
Remember?
yeah, I have submitted, but I refer some videos in YouTube where where they discussed about a method. Based on that, I calculated that. I think we didn't discuss in that class how to calculate the chip area. and all.
How to calculate the chip area? Yeah. So
From later.
yeah, the procedure is again simple here. You see, what people will do is a one method is that they will first like they want to do the flow planning, like I explained. So they will start with the bigger level first. Let's say this is the, they want to do the flow planning for the processor. right over here. Answer is here. So processor, so already they know that they want to design a logic for the processor. In the processor they have a architecture and the micro architecture. Then in each micro architecture they have a logics. In each logic they have a functional blocks. In each functional blocks they have modules, and each module they have these cells. If you remember, I explained you that. So they would first start with the cell. They will design themselves, or they would already access from the library, and they will decide which portion of this chip, for example, this is the portion they want to use, where they want to place it, and accordingly they will already by the hand calculation, like I taught you with the lambda rule, they already will know how much is the size of that unit cell, and using the unit cell they will keep on calculating the higher blocks that they are putting and in the area here, and accordingly they will keep calculating, and finally they would estimate the final size of this architecture as written over here. So for instance, using all things I just explained, I have created these blocks and I have placed this is the block for, let's say this is for the control and this is for the data path. So I would just know that roughly my size is 1900 lambda by 2550 lambda. Got it?
With some confusion. Sir, I will share that video with you.
I mean, this is how, with you ask me how to hand roughly estimate, right? So hand calculation is like this only. You don't need to use any software to estimate that. Of course, software can also do that, but this is how you will, the physical designer can think about roughly estimating the logic area.
Suppose we are considering a 3-input OR gate,
Yeah.
and that was a homework actually. We draw the layout diagram of that three-input OR gate, and from that we are finding this chip area.
Whole chip area from that unit cell.
That was the homework actually.
Homework was just to draw the layout of the unit cell, NAND, NOR and OR inverters, and using the lambda rule estimate the size of the layout. Wasn't it?
Estimate approximate chip area.
Correct. Yeah, so I said the chip was only for the unit cell. Chip wasn't for the whole processor.
That is the chip area for this OR only.
Yeah, this is the, in this slide, in this session today, the slide we are seeing, I explained you how to estimate the chip area for the processor.
Okay.
And the homework was just a unit cell.
Okay.
Understood?
Yes, sir.
Okay, so if there are no more questions, so we stop.